So in this video we are going to discuss the question in thermal physics which appeared in IIT-JAM 2008 examination. The first question is, the chemical potential of an ideal Bose gas at any temperature is. Okay, so this is basically a conceptual question. So the thing that you need to remember is that for boson, the chemical potential that is mu, either it could be 0 or negative. Okay, and as a special case it's 0 for the photon gas, please remember it. Okay, for photon gas, whereas for the fermion mu, it could be positive, negative, as well as 0 also. Okay, so just remember it. So here, because in the question it's asked for the boson gas, so it could be 0 or negative. Okay, so either 0 or negative, so therefore B is the correct option here. So let's continue with the next question. The statement is, a thermodynamic system is maintained at constant temperature and pressure. Okay, in thermodynamic equilibrium. Okay, so we have to identify the correct option. So in order to understand this problem, let's continue with the definition of the Gibbs free energy. Gibbs free energy, that is G, that is equal to H minus Ts, where H is the enthalpy basically. Okay, so here dg, a small change in G, gives free energy, that is dH minus Tds minus S dt. Okay, so here we need the value of dH, that's the change in enthalpy. So for this purpose, the H, we will go back to the definition of the enthalpy H, that is equal to U plus PV. Okay, so that means a small change in enthalpy dH, that is equal to du plus pdv plus bdp. So du is from first law of thermodynamics, so du is equal to tds minus pdv. Okay, so this is the expression for the du. Okay, it's derived from the first law of thermodynamics. Okay, now the next part, p dv plus v dp. Okay, so this pdv will cancel with this, so dH is equal to tds plus v dp. So we will make the substitution for dH here, so that is equal to tds plus vdp minus tds minus s dt. So tds and tds, they will cancel with each other, so we are left with dg, that is equal to minus s dt plus v dp. So that's the change in free energy. Okay, so now when T and P are constant, when T and P, both of them are constant, so this implies dt equal to dp, that is equal to 0, and which says that dg, it acquires some certain minimum value. Okay, so therefore here the correct option is Gibbs free energy, that is minimum. So A is the correct one here. And here let me add another remark here. In the if the same question is asked, if rather than temperature and pressure, if we say that temperature and volume, they are kept constant. Okay, so in that case we can prove that instead of dg, it's df, that is equal to 0. Okay, so when temperature and volume, they are kept constant, it's the Helmholtz free energy, which is minimum, whereas when temperature and pressure, they are constant, it's the Gibbs free energy, that is minimum. Let's continue with the next question. The statement is, an ideal gas kept in contact with the heat reservoir. So it's important to note this point. The gas is kept in contact with the heat reservoir. It undergoes a quasi-static process in which its pressure is doubled. Okay, obtain the Maxwell relation from the differential form of. So we are given the expression for the Helmholtz free energy, change in Helmholtz free energy, dF minus s dt minus p dv. Okay, let's call this equation as 1 and evaluate the expression for the change in entropy for n mole of a gas. Okay, so we will continue with the part A and then we will come to the part B in the after finishing part A. Okay, so here first of all we will identify the natural variables for the Helmholtz energy. So natural variables for F are temperature and volume. So these are so it's from the differential we can identify the natural variables. So that means we can write the Helmholtz energy in terms of its natural variables, which are T and V. Okay, so this means we can write a small change df that is equal to now we are going to write a small change in f in terms of its natural variables. Here because we are going to evaluate the Maxwell relation, so we are going to make use of another fact here. So we can write f as a function of t and v. Okay, and the fact that f, the Helmholtz energy, it's a perfect differential. This implies that the order of differential of f with respect to t and v, that doesn't matter. Okay, that is curly t of df by dv by keeping t constant, and outside we will have this constraint. This will be equal to curly v of curly f by curly t, v outside and t outside. Okay, so what does this mean? When we say that this is a perfect differential, so that means it's a path independent quantity basically. Okay, so that means it doesn't matter when we are taking the first differential with temperature or with volume, or when we interchange the order, its second order differential with respect to these two variables, it's going to be identical. Now from equation 1, let's call this as equation 2. From equation 1 we can also write that S is equal to minus df by dt by keeping volume constant. Okay, similarly I can write P. Okay, so when I keep the volume constant here, so dv, this will disappear, dv is equal to 0, so then S is equal to df by dt. Similarly from this equation P is equal to minus df by dv by keeping temperature constants. Now plug in these value here, so this one here and this one here, and when we do that we obtain the required Maxwell relation. So that is dp by dt at constant volume, that is equal to what? ds by dv at constant temperature. So this is the required Maxwell relation. So let's call this as equation 3. Okay, now we have obtained the Maxwell relation from here, and evaluate the expression for change in entropy for n mole of ideal gas. Now we will come to this part. Okay, now for n mole of ideal gas we can write PV, that is equal to nRT, and from here P, that is equal to nRT by V. So this implies dp by dt by keeping volume constant, that is equal to dp by dt, that is equal to nr by b. Okay, so let's make use of equation 3 and 4. So that means for the ideal gas, so that is ds by dv at constant temperature, that is equal to dp by dt, that is equal to dp by dt at constant volume, and this is equal to this quantity, that is nr divided by B. Okay, now because this is at constant temperature. Okay, now as the ideal gas, it's also in contact with the heat reservoir, because ideal gas is in contact with heat reservoir, so that means temperature doesn't change. Okay, and if that is the case, we can write this equation. So this, I'm talking about this equation. Let me go to the next page. I can write this equation as ds, that is equal to nr dv by db. Okay, so because the pressure of the gas, it's given that in the statement, it's given that the pressure of the gas, ideal gas, it's doubled because pressure is doubled. So that means what will happen to the volume? So that means if pressure of the ideal gas, it goes to 2p, so that means to keep this equation valid, PV is equal to nRT. When pressure is doubled, so that means volume will become half. If volume, initially the volume is V0, it will become V0 by 2, so that this equation is valid. So in that situation, delta S will be nR from some initial volume V0 to V0 by 2, and then dV by V, and that's nothing but nR ln final volume, which is V0 by 2, divided by initial volume, which is V0. Okay, so that means after solving, we will obtain that this is equal to nR minus nR ln 2, because here we will have B0 and B0, they will cancel with each other, so we will have ln 1 by 2, so that will give a minus n ln R2. That's the change in entropy of the gas when its pressure is doubled. Okay, so this example also highlight the importance of the Maxwell relations in to evaluate the corresponding entropy change in certain situations. So we will continue with the second part of this question. The first part we have already done. Okay, so let's pay attention to the second part. So using S, that's a function of T and V, derive a general expression for du by dV, that's change in internal energy with volume at constant temperature, where internal energy, it's a function of S and V. Okay, is the internal energy basically. Okay, evaluate it for the ideal gas as considered in part A. Justify that the outcome is consistent with the expression for the average energy known from the kinetic theory. Okay, so from the given information here, we will try to connect the internal energy change with various variables. Okay, so the first information that's given to us in this question is that entropy, it's a function of T and V. Okay, so that means with this information, what we can do is S, it is a function of T and V. Okay, so this allows us to write a small change in entropy ds, that is equal to ds by dt by keeping other variable constant, and then dt plus now the change in the entropy now, but with respect to the second variable, ds by db and dv by keeping other variable constant. So let's call this equation as equation 1. Okay, now further, it's also given that u, it's a function of s and v. Okay, so from here, as we did for entropy change, same way we can calculate the small change in internal energy, and that is equal to du by ds by keeping volume constant ds plus du by dv by keeping s constant. Okay, now here we will substitute here the ds value from equation 1 here, and then we'll see that this is equivalent to so the first differential, that is du by ds by keeping volume constant, and then the value of ds from equation 1. Okay, which is ds by dt at constant volume, and then plus the second term ds by dv at constant temperature multiply by dv. Okay, so now this term is complete. Okay, now the second term plus du by dv at constant entropy, du by dv at constant entropy multiply by dv. Okay, so from this equation we can rewrite it further as this is equal to, now we will bring du is equal to, this is equal to this expression, this entire expression. Okay, now we will bring dv on the left hand side and then put a constraint of constant temperature. Okay, because that's what we are asked, du by dv at constant temperature, that's asked from us. Okay, so from here we can write du by dv at constant temperature. So when we put the constraint of constant temperature here, so this term will disappear, so this will become 0, dt will become 0 here. So this is equal to basically du by ds at constant volume, and then this is 0, and then this term. Okay, so ds by db, ds by dv at constant temperature plus du by db at constant entropy. Yes, that's all. dv we have already taken on the left hand side, so this dv also we took to the left hand side. Okay, so let's call this as equation. Okay, so we call this as equation 2 and this as equation 3. Okay, now we'll make use of the first law of thermodynamics, which says that du, that is equal to tds minus pdv. Okay, so from this equation we can write t is equal to du by ds, t is equal to du by ds by keeping volume constant, and p is equal to minus du by db by keeping s constant. So this is here we are going to replace it with the p. Okay, so with this substitution we are going to substitute this in equation 3. So if we call these results as equation 4, so 3 and 4 implies, so equation 3 and 4 implies this is equal to t du by ds at b. So we are going to replace this quantity with t. So t ds by db, t ds by dv at constant temperature plus du by db. So this is equal to minus p. So here instead of plus I am writing here minus p. Okay, let's call this as equation 5. Okay, let me introduce a page again here. So let me write the final result that we just obtained. We have obtained du by dv at constant temperature, that is equal to t ds by dv at constant temperature minus p. Okay, here we are going to make use of the one of the Maxwell relation. What is that? ds by dv at constant temperature, that is equal to dp by dt at constant volume. So with this substitution this is equal to t dp by dt at constant volume minus p. So this is one of the standard result, du by dv at constant temperature. Okay, so here this is our final result. Now we are going to evaluate this for the ideal gas equation. Okay, so for an ideal gas we have PV is equal to nRT. Okay, so from here dp by dt that is equal to nR by B. Okay, so therefore with this substitution here, so we are going to substitute it here. So this is equal to du by dB du by dV at constant temperature, that is equal to nRT upon V minus P, and that is nothing but P minus P, and that is equal to 0. So what does it mean basically? Okay, so that means the change in internal energy of the ideal gas with change in volume at constant temperature, that is equal to 0. Okay, so this means that internal energy or internal energy U of ideal gas is not a function of volume. It is a function of T only, and that's what we also learned from the kinetic theory of gases. Okay, so that's what it was asked in the statement of the problem. So let's continue with the next question. The question is, consider an ideal Fermi gas consisting of n non-relativistic spin-half particles which are confined to a length L in one dimension at absolute zero. Okay, so the first point is find expression for the density of states and hence calculate the Fermi energy of the gas. The second is find the mean energy per particle in terms of Fermi energy. Okay, so let's continue the first part. So we are given a system of n non-relativistic spin-half particle, and when they are confined to a length L in one dimension, the corresponding energy eigenvalues, the allowed energy eigenvalues for particles that are confined in one-dimensional box of length L are, they are given by E, that is equal to n square h square upon 8 m L square, where n can take value from 1, 2, 3, so on basically. Okay, so this implies n is given by n, that is equal to L by h multiply by 8 m e power 1 by 2. Okay, let's call this as equation 1. Okay, if we just pay attention to the n, because here n it's changing by 1 unit. Okay, so that means basically this number n, it gives us the possible number of microstates, or you can say the energy states. Okay, because it's changing by unity, changes by unity. Okay, so its values, they will give us the number of microstates in particular with energy less than or equal to E. Okay, so that means if omega denotes the number of microstates or the energy states with energy less than or equal to E, so that in that case omega dash E, which denotes the energy states in the interval E to E plus dE. Okay, so omega dash E, that is equal to dN by dE multiply by dE. Okay, and then if you consider the degeneracy also, then we need to multiply by the degeneracy factor also. So this is equal to G dN by dE. So that means G multiply by L by H and then 8m power 1 by 2, and then differential of E power 1 by 2 with respect to E. Okay, so 1 by 2 E power minus 1 by 2 dE. Okay, this is equal to G L by H 2m by E dE. Let's call this as equation 2. Okay, so here G, that is equal to 2s plus 1, and for spin half particle this comes out to be equal to 2 into 1 by 2 plus 1, that's a 2. That's a degeneracy factor. Okay, so therefore omega dash is equal to, therefore omega dash E, that's the energy states in the range from E to E plus dE. Okay, that is equal to 2L by H into 2m by E under root multiply by dE. So this implies GE, that's the density of states, that's simply this value. Okay, so density of states, that is equal to 2L by H multiply by 2m by E power 1 by 2. Okay, that gives us the density of states. Okay, now in order to calculate the Fermi energy, we need another information which is called as the Fermi. For fermion, the distribution function is, let me go to the next page. The distribution function for fermion is given by f of E, that is equal to 1 over 1 plus exponential E minus EF by KT. Okay, and this is equal to, depending on the situation, this is equal to 1 for E less than EF at absolute 0, and this is equal to 0 for E greater than EF at T equal to 0 Kelvin. Okay, so we will make use of this fact, and then we will try to evaluate the Fermi energy and then the average energy. Okay, so the total number of particles in the system is given by n. We note that as n, and that is equal to 0 to infinity, the probability distribution function which gives the probability, and then if you multiply it with the density of states. Okay, so that will give you the occupancy, basically the total number of particles. Okay, and this can be written as, this is equal to, so we are going to split the integral into two intervals, 0 to EF, f of E GE dE plus EF to infinity f of E GE dE. Okay, because for E greater than EF, okay, so this will be 0, so this integral will become 0. So we only need to worry about the first integral. Okay, and this can be easily evaluated because Fe for energy less than EF, so this is equal to unity here, this point. Okay, and then we will simply substitute the value of GE as we have obtained in the previous slides, so this value. Okay, so then we can quickly evaluate the number of fermion in the system, and that is equal to integral 0 to EF 1 multiply by 12 by H 2m by E power 1 by 2 dE, and that is equal to, it's not 2, it should be 4, I think. Let me check. 2L upon H. Okay, yes, that's 2. So this comes out to be equal to 4L by H. So here another factor will come from the, when we will perform the integration. Okay, so 1 by 2 factor that will come from there, so that's why here it will become 4L. So 4L by H 2m EF power 1 by 2. Okay, so that means n is equal to 4L by H 2m EF power 1 by 2. So this gives the total number of particles in terms of Fermi energy, and from here we can invert this relationship and write the expression for the Fermi energy, and that is equal to NH upon 4L and 2m, and its square basically, and this is nothing but n square h square upon 32 m L square. So that is the expression for the Fermi energy. Okay, so okay, now we need to find the mean energy per particle. Okay, so let's put another slide here. The mean energy, in order to calculate the mean energy per particle, mean energy per particle. Okay, so let's see how we can do that. So mean energy per particle, E, that is equal to 0 to EF, E, and then F of E, GE, DE divided by 0 to EF, F of E, GE, DE. Because we are evaluating the integral from 0 to EF, so this will be unity and this will be unity, as I just mentioned in the previous slide. So this and the common term, because here we are having GE here and GE here also, so constant terms, they will cancel with each other. So we will be simply left with here in this integral 0 to EF e power 1 by 2 dE, and in the denominator we will have 0 to EF e power minus 1 by 2 dE. Okay, so this will come out to equal to EF power 3 by 2 divided by 3 by 2 multiply by 1 by 2 divided by EF power 1 by 2. So some of the terms will cancel with each other, and ultimately we will be left with EF divided by 3. So that means mean energy per particle is 1 by 3 of Fermi energy. That's the final result. Please note that this problem can also be discussed in solid state physics also, because some of the concepts here they are involved from the statistical mechanics. So that's why I prefer to discuss it here. So let's continue with the last question from IIT-JAM 2008. The statement is: consider a system of n non-interacting distinguishable spin-half particles. Okay, so this is important to note that the particles that are given to us, they are non-interacting and they are distinguishables. Okay, each of magnetic moment mu. Okay, the system is at an equilibrium temperature T in a magnetic field V, such that n particles have their magnetic moments that are aligned parallel to magnetic field. Okay, so what we are supposed to find out is find the energy E and entropy S of the system. Okay, using the relationship between E and S, find T, hence determine the ratio n by n in terms of mu, V and T. Okay, and then we are also given that we have to make use of the Stirling approximation here. Okay, so this problem can be solved in a very simple manner. So the point is that when a magnetic moment it's placed in a magnetic field, the interaction energy, okay, so the energy of interaction of spin having magnetic moment mu, that is given by, or if I call that energy as E, so that is equal to minus mu the magnetic moment dot B, the magnetic field applied. Okay, so for spin half particle there exist two different energy states. Okay, for spin half particle some of the spins may align parallel to the field direction and some of them will align in a direction opposite to the field direction, and if we call that energy of interaction as E1 when spins are aligned parallel to the field direction. So that means when spins are aligned parallel to the field direction, so that means the angle theta between mu and v, that's equal to 0. Okay, so mu v cos of 0, so that will give minus mu v. So E1 and the energy of interaction in that case is, let me call the energy of interaction as minus mu v when mu it is parallel to magnetic field. Okay, and let's call the energy as E2 when the magnetic moment it is anti-parallel, it is anti-parallel to v. Okay, so that means theta is equal to 180 degree here. Okay, so when theta is equal to 180 degree, the cos 180, that will give another minus sign, so it will become positive. So this E2 is equal to plus mu v in that case. Okay, so we are given that out of total n spins, out of n, it is given to us out of capital N are aligned parallel to B. Okay, so that means the energy of interaction is given by E, that is equal to the n times the energy of the spins that are aligned parallel to the field, so n times E1 plus remaining n minus n spins which are aligned and anti-parallel to the field having energy E2 each. Okay, so therefore E is equal to the net energy, that is equal to n E1 is minus mu v plus n minus n multiplied by E2, which is mu v. So after solving we obtain that this is equal to n minus 2n multiplied by mu v. So that is the energy of the system. So this is one of the answer that's asked in part A. So let's call this as equation 1. Okay, now in order to determine the entropy of the system, we need to find the possible microstates. So that means a situation from in which out of the n spins are aligned, small n are aligned parallel to the field and n minus n are aligned anti-parallel to the field. Okay, so therefore possible or feasible possible number of microstates are, if it they are n, c, n. Okay, and if we denote those microstates as omega, that is equal to n c n, that is equal to arrangements of n objects, that's n factorial, and out of which n factorial are of one type and remaining n minus n factorial they are of another type. Okay, so that will that is the possible number of microstates. Okay, therefore the entropy from the Boltzmann relationship, that is equal to S, that is equal to kb ln omega, and that is nothing but kb ln n factorial upon n factorial into n minus n factorial. So this is the expression for the entropy. In principle, this can be expanded by making use of the what you call as Stirling approximation, and if we do that, the entropy is given by S, that is equal to kb now ln n factorial, so that is equal to n ln n minus n. Okay, and then divided by n factorial, so that means a negative sign will come here, n ln n, and minus will become plus basically. Okay, so plus n, and then ln of 1 upon n minus n factorial, so that will give us minus n minus n ln n minus n, and then minus will become plus n minus n. Okay, so some of the terms will cancel, so here it's minus n, it's plus n, it's minus n, and it is plus n. Okay, so this is equal to kb n ln n minus n ln n minus n minus n ln n minus n. So this is the expression for the entropy. Okay, now in order to to obtain the results for the second part, so we need to we will figure out two differentials of the entropy with respect to n and the differential of energy with respect to n, and then we will connect these two differential to determine the temperature. So let's try to understand this by through these steps. So first of all, we are going to determine what is the value of ds by dn, okay, at fixed volume. So here remember that n, this number, it's not fixed, it can have any value. So that's why we are differentiating, we are trying to maximize the entropy with respect to n here. Okay, and here let me call this as equation. Let me check what equation number. Okay, it's 2 I have already given, so let's call this as equation 3. So now we are going to differentiate equation 3 with respect to small n by keeping v constant. So kv outside as it is. The first term will give you 0. So here, well, it's basically with respect to small n. So then minus ln n minus 1. So here it's from this expression, if you differentiate it with respect to small n. Okay, plus from here n minus n, and then sorry, it is plus sorry, this should be ln logarithmic. Okay, let me cancel it, minus 1, and then we will have the ln n minus n term. Okay, so here, because here we will have minus, and when we will differentiate this minus n with respect to n, minus 1 will be there, so minus minus will become plus. So ultimately we will be left with ln n minus n, and then we will have another factor of plus 1. Okay, that will come from this term. Okay, while doing differentiation with respect to small n. Okay, so after rearranging these terms, we will obtain ds by dn at constant v, that is equal to kb ln n minus n upon n. Let's call this as result 4. Okay, also from equation 1, what is the equation 1? That's the total energy of the system. So from this equation we will obtain dE by dN. Okay, so dE by dN, it is from equation 1. Okay, so dE by dN at fixed volume. Okay, so this is equal to minus 2 mu v. Okay, why minus 2 mu v? So here it's dE by dN, so minus 2 then mu v. Okay, so let's call this as result 5. Okay, so now these two results, that is equation 4 and 5, so 4 and 5 will give us ds by dE, that is equal to ds by dN at fixed volume divided by dE by dN at fixed volume, and that is equal to kV ln n minus n upon n. So this result, okay, equation 4, and then divided by dE by dN, which is minus 2 mu v. Okay, now ds by dE, that is equal to 1 by t. Basically it's a standard result, it is 1 by t. Okay, so 1 by t, that is equal to ds by dE. So this equation gives us, so after rearranging all these terms, so I'm talking about this one. So after rearranging, we obtained ln n minus n upon n, that is equal to minus 2 mu v upon kt. Okay, so taking the exponential, this gives n minus n upon n, that is equal to exponential minus 2 mu b upon kt, or this implies that capital N by n, and then from here we will have minus small n by small n, minus 1, so it will become plus 1 on the another side. So 1 plus exponential minus 2 mu b upon kt. Okay, so this gives us small n by n, that is equal to 1 upon 1 plus exponential minus 2 mu b upon kt. So this is our final result.